Hi everyone, once again I'm speaking here about the integrated deformation profile of the ice mass. In this case I'm concentrating on the alpine glaciers mainly in these examples, so you can think about how ice sheets can be much larger, they can be much flatter. These are alpine glaciers where we see that the ice is confined in a certain valley that the glacier would create. And in both cases, these are much smaller than if we think about what we see in Antarctica or even how ice streams are acting. But I want to get back a little bit to the deformation profile, which is integrated. We said that there will be different forms of motion, and then I just label these and put here so what this will be about. Some of you were asking, and why I cross some of these out, because the integrated deformation profile will be different in the case of the different types of glaciers or ice masses, and in this case it's mainly about the presence of water and the bedrock itself. So there will be a deformation in the first place of the ice, there will be a basal sliding, and there will be a bed deformation as well. And depending on whether these exist, what kind of ice mass we're talking about, then the integrated deformation profile will be different. So I just put here, this is the ice deformation. This is the basal sliding. And that will be then the bed deformation. And what you see here is the integration of these three possible components of the movement of the ice. So what do I see over here is different velocities. So this actually is a little vector here. The little arrow shows the movement that is possibly happening. And if I just come to the top over here, what it means that at one point of time, perhaps the January 1st, this year, we check where the ice or how the ice is located, this point of the ice on the top of the glacier, and then a year later we check where it will be. So that's how I just put here this movement over here, which we see 1 year later. It says that the top of this glacier, and perhaps here in the central line, the medial line, it will be 50 plus 10, so that will be 60 meters of movements altogether that would happen. Now I just randomly threw these numbers here, so that shouldn't cause you trouble to imagine these movements, and they're really random. I just put them here, so that's what this would mean in the case that we both have the bed deformation, the basal sliding, and the ice deformation itself. But usually, obviously, these would be differing in real life. So what I can just then do or say is that this will differ depending on what kind of glaciers we have. Now, over here, you see this little drawing, so I just copied this from my earlier slideshow from last class. You see this one, and it's an anatomy of a alpine glacier. I'm going to label this for you later on, but the point here is that this is a warm ice glacier. What does it mean it's warm, or what can the temperature at all depend on? We said that there might be all kinds of different sources of this meltwater basically that can exist over here on the bottom. So between the ice and between the bed, this can be warm base glacier if there is water film, and if we have water film, then the basal sliding will also exist. And we said that there are examples. This is also a drawing from my earlier lecture. It's the Dry Valley from Antarctica. You see this little image here, and I said that this glacier will be motionless. It's mainly not melting, but it's sublimation that causes ablation over here. So in this case, we say that basal sliding is not happening. There is no water between the rock and the ice itself. And again, what sources of this heat can be the composition of the ice, so the solubles, salt, and so on. So what is the pressure melting point and how this is affected by the ice material itself. It can be the weight of the ice, so the pressure itself. It also can be because of the temperature. So we said that these glaciers that are in the temporal zone, like in Europe or Alaska, will be able to move much faster than those that are, for example, in Antarctica, which is much drier as well. So that's why in this case sublimation can be much stronger. So depending on these factors, whether we have water or not, water film between the ice and the base, the bedrock, they can be moving in different ways and at different speeds. So again, temperature, pressure itself, the relationship between the two. It can be the climate overall, so the air temperature. It can be also the generation of meltwater through the surface melting. So there are various different factors that can play a role here. And so for this case, I'm just going to draw this again very quickly, integrated deformation profile. If I say that there is basal sliding because it's a warm base, so I put here warm. We're talking about warm base glacier, and we also say that ice deformation will often happen in itself. That's fine, but that bed deformation can also happen if here this is sedimentary rock. So it's something like the till material under the ice. It's not a piece of granite. So that's why I just put that it's like unconsolidated sediment. So it's not the hard parent rock under it. Then these three can act or play a role. And again, what this will mean, this is the surface, as I said over here. This is the point where that little red point is, at one point in time. So that's the starting point. And what this will, or how this will move, well, right here, then I just say that there will be ice deformation, basal sliding, and bed deformation. I'm starting this with this one over here. So this material over here, under the ice, it's made of rocks, it's made of sand, pebbles, cobbles, whatever, will be moving. Over here, there will be a component of this movement based on the transformation of this bed. Yeah? So it will be slipping the ice on the surface, but at the same time it will be squeezing and pulling some of the material under it with itself. So there's this kind of change. And there will be then basal sliding, so it's simply the ice slipping on the water film between the bed, the ice itself. So there will be one more component. So this is another little velocity vector over here. And there will be the ice deformation as well. So that will be something like, as we said, like this. That will be a higher volume on the top and a lower volume on the bottom, because there is still friction, independently from the fact there is the sliding over here. So that's why we can put these different vectors over here. And then overall we will say that on the very top of the glacier, the speed of the movement will be faster. So that's the new point where this piece of ice will be located, or the surface of the ice will be located in a year's time. And obviously this can be like 10, 20, 30 meters per annum per year, but this can differ. So these are just random numbers that I put here. And obviously, most cases, I might say that it's the basal sliding that would be the most in real life, but I just don't want to draw so long integrated deformation profile here. Okay, so that's one case that I was talking about. And how about this one? So here, this is going to be, I just put again, cold. Although I could use different colors. Cold, and this is the hard bedrock. Hard bedrock over there. And what else is different then? We might say that there is a different climate, so there is, again, no meltwater, but also we can say that this ice is much smaller, it's not as thick. So if I want to be proportionate, and I'm going to draw this one over here as well, so this is what belongs to this drawing then, the same. If I want to be proportionate, I might say that this is not as tall. So you see, this is a thicker ice. The thickness will cause a stronger deformation, stress, apply stress. But this is at all, perhaps in this case, going to be less thick. So how is movement happening over here? And I say that the movement might be very small. So compared to this, which we said can be things like 100 meters or whatever, over here we might say it's only just like 10 meters. That will mainly be about perhaps only the ice deformation, which I just put here. Ice deformation, something like this. And again, to be proportionate, I draw it much smaller. Last time I was drawing a little something over here. So just to make sure, this is again this point and the new point, which is the top one over here and the bottom one over there. And the movement, or the vector, will be this way. So again, from left to right. And what else do we have? If I said it's cold based, there is no basal sliding. Now this is what I did last time. So I said, okay, we're crossing out this one. There is no basal sliding. So that doesn't apply. Here we have ice deformation, no basal sliding. And do we have bed deformation? If it's a hard rock under it, perhaps it is, then that will not be moving. So there will be no drag here of this material. The bed itself is not sliding over there. And that's why last time in my little video I was crossing out this one like that. If it is a hard bed. Yeah, so these are two different regimes, and obviously you can combine. Is it cold, hard, warm, or to what extent is it going to be thick ice? So to what extent will there be a pressure, in this case, for the ice to deform itself? And in this case I said a small glacier that we're talking about. You might remember the glacierette in my first class about the glaciology. And the glacierette is going to be a very small piece of like ice. It's like a fern. It's not actually a glacier, it's just a piece of ice existing somewhere in a higher altitude, but it's not really a glacier, it's not really moving. So that's how you can imagine this one to be similar as well.